Your legacy tools don't need to stay stuck in the past. Modern MCP clients can handle them gracefully without breaking changes. We'll see how FastMCP's fallback behavior automatically adapts when structured output isn't available, letting you process both modern schema-based results and raw content blocks from the same response. The pattern ensures backward compatibility while still giving you access to rich, typed data when it exists.
Async with client. Result equals await client, call tool, legacy tool, param, value. If result data is not none. Hash structured output available and successfully deserialized. Printf structured, result data, else. Hash no structured output or deserialization failed. Use content blocks. For content in result content. If hasheader, content, text. Printf text result, content text. Elif hasheader, content, data. Printf binary data, len content data, bytes.
This demonstrates the dual result handling pattern for RPC systems, where a single call can return both strongly typed structured data and fallback content blocks. The pattern distinguishes between machine processable outputs and human-readable representations, ensuring compatibility across different client capabilities. What makes this distinctive is its graceful degradation. Clients get the richest available format while maintaining access to raw content when structured parsing fails. The approach works by treating structured data as the primary result while preserving traditional content blocks as a secondary channel. FastMCP automatically hydrates complex types from schemas when available, but falls back to raw text or binary content when schemas are absent or deserialization fails. This separation of concerns lets servers evolve their output formats without breaking existing clients, as older consumers can always access the content blocks. This pattern solves the versioning problem in distributed systems where servers and clients upgrade at different rates. It's particularly valuable for AI integrations, legacy system compatibility, and progressive enhancement scenarios. The trade-off is slightly increased complexity in result handling, but the benefit is future-proofing your API against schema changes and client diversity. Let's break it down line by line.
Async with client.
Async context manager pattern ensures the client connection is properly initialized and cleaned up after use, preventing resource leaks. The async with syntax handles both setup and teardown automatically.
Result equals await client, call tool, legacy tool, param, value.
This invokes the legacy tool via RPC, passing parameters as a dictionary. The await handles the async operation, ensuring non-blocking execution while waiting for the tool's response. This is the standard pattern for calling FastMCP tools from client code.
If result data is not none.
This checks for structured output availability. The result data field contains deserialized structured data when the tool call succeeds, and this guard clause ensures we only process it when present. Without this check, we'd risk null reference errors when tools return unstructured content.
Hash structured output available and successfully deserialized. Printf structured, result data.
This handles the success case where the tool returns structured data. The result data field contains the deserialized output, ready for direct use in Python, no parsing needed. This is the preferred path when tools return typed responses like JSON or protocol buffers.
Else.
This else branch handles the fallback case when structured output is unavailable or deserialization fails. It processes raw content blocks instead, ensuring graceful degradation when the tool doesn't return structured data. This pattern maintains robustness by handling both success and failure modes explicitly.
Hash no structured output or deserialization failed. Use content blocks. For content in result content,
This implements the fallback content handling pattern. When structured output fails or doesn't exist, it iterates through raw content blocks to extract usable data. This ensures you always get results, even from legacy tools with inconsistent output formats.
if hasheader, content, text,
This performs dynamic attribute checking to determine if the content object has a text attribute. It handles heterogeneous result types safely, preventing attribute error when processing mixed text and binary responses from the tool call.
printf text result, content text,
This handles text-based content blocks from the tool response. When the structured data field is unavailable, it extracts and prints the raw text output, ensuring you always get human-readable results from the tool execution.
elif hasheader, content, data,
This checks for binary data content using Python's hasheader, handling cases where the tool returns raw bytes instead of structured text. The pattern safely distinguishes between different response types without raising exceptions for missing attributes.
printf binary data, len content data, bytes,
This handles binary response data from the tool call. When the response contains raw bytes instead of structured data, it prints the byte count for inspection, ensuring you can verify non-textual outputs like images or files. This pattern safely handles all possible response types without assuming JSON structure. Structured data fallback pattern. FastMCP's dual output system automatically handles both modern structured data and legacy content blocks, ensuring backward compatibility without sacrificing new capabilities. The data property returns none when either the tool lacks a schema or deserialization fails, forcing you to check both paths. Always implement the fallback loop for content blocks when working with legacy tools or uncertain schemas.
The schema that disappears becomes the data you always find.